Okay, so this was our last speaker from overseas, and we're now going back to Sydney. And the speaker here was actually supposed to be physically here. Unfortunately, he caught a pretty serious cold and is staying home rather than infect us. Fortunately, he's feeling up to give the talk at least, as opposed to having to bail out. So our next speaker is again Google, so this is the Google session. And it's Rob Pike, who is a distinguished engineer at Google. He was many years at Bell Labs. He is the co-creator of Plan 9 from Bell Labs, which was, if you like, a logical successor to Unix, built on very much the same principles of terseness, simplicity, being able to combine things, but basically extending the Unix model onto distributed systems. And specifically, Rob was the author of the Plan 9 Windows system called 8.5, which was very much opposite to what was then the dominating thing in the Unix world, X Windows, known for being bloated, and whereas the whole Plan 9 Unix tradition, of course, is the exact opposite. And at one stage, Rob made this remark about X Windows. He's never seen something fill a vacuum so quickly and still suck. Meanwhile, he has moved on to Google quite a while ago, and they are doing more mischief. In particular, created the Go language, or co-created the Go language, which is a programming language specifically designed for distributed systems, and again, very much built on this notion of really keeping things simple. It's widely used, not necessarily all for distributed systems, but actually container programming seems to be the dominating use these days, and it's of course open source. And I welcome Rob, who is now here and hopefully fit enough to talk.
Thank you very much. Can you hear me okay? All right, I'll assume you're hearing me. Thank you, everyone. It's really nice to be here. I certainly wish I was in the room, which was my plan. I was looking forward to that. Yes. It's very nice. In fact, gave a talk at UNSW quite some time ago on a precursor language to this, so it's kind of nice to be back at UNSW, at least virtually. And like all of you, I'm here because of John Lyons, but what that means for me is probably a little different from what it means to you. When I was a student at the University of Toronto, I naturally had the samizdat copy of the Lyons book. When I got to Bell Labs in the 80s, I managed to get the official Bell Labs version of that, which was a really nice thing to have, and I still treasure. And in fact, I got my very own copy signed by John Lyons when he visited the lab some years later, which made me very happy. But there's more to the story than that, because I was actually my whole career depends on an encounter with an Australian in a ski chalet. Ian Johnston bumped into me at the Boulder Usenix conference when we were both not skiing and sitting in a ski chalet having a drink. He invited me to interview at Bell Labs, and I went there, and that was just the most amazing thing to start off a career. And of course, Ian is Australian. While he was there, he brought along with John Lyons' encouragement, a number of people from Australia to Bell Labs to learn about Unix and bring the ideas back. There became a real conduit between the Australian Unix community and Bell Labs because of that. And so as a result, eventually I found myself in Australia on a visit. I kept visiting, and I just stayed longer and longer. And at this point, basically all that's happened is I've stopped leaving. So I'd like to thank John for setting all that up and making, in a very real sense, my career possible. But I'm here to talk about Go, and I'm sure most of you know a little bit about it. I'm not going to teach you Go today, because I'm not really going to talk about the language as a language that much. I'll have to do it a little bit. But instead, I'm going to talk about what shaped the language, and especially all of the things around it that make it as successful that it has been. And it's definitely not a mainstream language, but I think it far exceeded our expectations in terms of how much it's taken off in the world. So first of all, for the programming language crowd in the room, yeah, you're right. It's not a very interesting language. We get that. We knew that at the time. It was not a language that had technical advances. We weren't trying to advance the cause of programming language theory or design or even practice. But we were okay with that. That wasn't our goal. Yet somehow the language has managed to, as Gernot said, take over the cloud world. It's the language behind Docker, Kubernetes, essentially everything in the Cloud Native Computing Foundation, and lots of other stuff out there. Envoy, Pantheon, goes on and on. And as someone said some years ago, but in the future tense, but now in the present tense, Go is the language for cloud infrastructure. And so there's this question, how did a language that nobody liked essentially end up becoming so important? Well, it's because the success of a language depends on a lot more than the language itself. And we were aware of this from the beginning. We did not want to make just a new programming language. We wanted to build a better way to write software that dealt with some of the problems that the programming languages we were using at the time were struggling to deal with. Things like the very large scale we were working with, security and safety of the execution, management of dependencies in a controlled way, predictable performance, high portability, lots of tooling with automation of changes, which is something we do a lot. Having libraries that you could really lean on and trust them in production. And a guarantee we wanted of long-term stability of everything, so that once you built something, you knew it was going to continue to work. And although some of those things can be influenced by the language, and in fact, I gave a talk some years ago about how the language was driven by some of these considerations, there's much more to it than that. So let's look at a little bit of history. Why did Go happen? Well, Ken Thompson, Robert Griefson, and I were sitting at Google one day in 2007, and we were kind of fed up. The languages that we were using, which were mostly C++ and Java, and particularly the environment in which we were working, which was pretty much what the languages drove you to create, were not really a very good fit for the kind of software we were building, which we would have called servers. Now you'd call it cloud. And we just wanted a better way to get work done. We wanted to be more effective. And we knew that to do that, we need a new language that enabled a better approach to building software. So although we definitely started with a language, there was a bigger vision all along. In fact, the syntax of the language came much later than you might think. We were thinking more about what it meant because we had this big picture. And when I say big, I mean big, because one of the biggest problems we had to deal with was scale. And scale had multiple axes. First of all, there was concurrency. In 2007, which is when we had our first conversation about this, there were multi-core CPUs showing up in our production clusters, but there was basically no mainstream multi-core languages that could light them up properly. There were threading models, but the libraries that used them were difficult to use. There were even papers. There's a famous one by John Ostrout that says, don't use threads, they're terrible. We pretty much were forbidden from using threading in our production code. That's not quite true, but there's a lot of truth in that statement. Instead, we were just told launch multiple binaries on the same machine and have the two binaries live side by side on multiple cores. And so as a result, we had these massive compute clusters, but they were very poorly utilized because the software couldn't make them work well and couldn't coordinate well within a multi-core CPU. Another axis of scale was simply engineering. There was, of course, a massive number of machines in production, a scale that I think is difficult to grasp for even for those of us who'd seen the data centers. But also programming. There were thousands of programmers all working on the same single code base. It wasn't like Git. It's a single system, and everybody works ahead, which means that there's countless changes every day across the entire ecosystem, and your code typically was affected by them constantly. So keeping up with all of that required a certain amount of discipline, but also a sort of speed of execution that we were struggling to make. And we couldn't really bring tools to help because the languages we were using were too difficult to automate. C, C++ in particular, but to some extent Java, it's just too hard to build tools to drive them, to automate, to understand what the program is doing, to understand its behavior, its dependencies, its security. And so we wanted tools that would make it easier to do that, but the languages were slowing us down in building those tools. There's also a scale of dependencies. I think I can say without fear of too much contradiction that Java and C++ are slow to compile. We actually made a measurement back in 2007 where we took a big binary in C++ that we had. It was a web front end. And we concatenated all the files together and saw how many bytes there were. And then we instrumented the compiler to see how many bytes it actually processed after going through the C preprocessor. And the answer was 2,000 times larger than the length of the files we were giving to the compiler. And, so we were literally compiling gigabytes of code. And in that, there were thousands of times that the compiler was taught what a string was or what a network connection was. And it just seemed like such a cumbersome way to build. Moreover, because of the lexical nature of the C preprocessor, it was very difficult to know if a dependency was even necessary. You could remove a dependency's include line, but the program would probably still build because chances are something else inside your tree brought that dependency in again. And so trying to eliminate dependencies was essentially infeasible. And evidence for that was a few years before we made a transition from the build system called Google 2 to the one called Google 3. And Google 3 let you specify the binaries much more precisely, not necessarily more correctly, but at least precisely. And we saw a 40% reduction in binary size by compiling the same code just because of the improvement in specifying the dependencies, which implies that at least 40% of the code in the old Google tip binaries was completely useless, and yet we couldn't find it, so we couldn't eliminate it. So let's take a step back. It's September 2007. We sketch on a whiteboard one afternoon, and if you were to stand in that room with us through the Wayback Machine and looked at the board, you'd probably see something very close to what Go is today, at least with a little bit of adjustment. The syntax and semantics were kind of in there. We knew it was going to look, we have brace brackets, but not a lot else. We knew that concurrency was critical, that packaging, in order to understand dependencies, was going to be critical. We didn't even talk about whether it was going to be garbage collected. We may well have assumed it, but we certainly didn't argue about it. We knew that tooling was important, and I'm pretty sure, and I think I can prove, on the first day, we were talking about having an automatic code formatter. That is, we were going to eliminate the whole question about where the spaces go by doing it all automatically, and that was part of the plan from day one. So let's look at a little bit of code. This is a simple hello world in Go, but this one, unlike the typical one, is actually a web server. So this is actually, in a way, I don't mean to minimize deployment issues and other things, but in a way, this is a production-ready web server that says hello world when you connect to it. So over here, it says package main. That's a statement. Package is a definition of what the component of build is. Main is a signal that this is where the program starts, approximately. There's an import clause that specifies two packages by these strings, FMT or FUMT and NetHTTP. And given those imports, there are two functions. The main function, which just calls the HTTP packages listen and serve function with these two arguments. The second argument is itself a function wrapped inside another function wrapper. But here's the meat of it. This is the thing that prints hello world. And so there's a fair bit going on here under the covers, although it looks fairly simple. There's a couple of imports. There's some use of things. There's some types coming in, but they don't have to be declared up here. They come automatically. In a package, you get the entire contents of the package from the package when you bring it in. You don't have to declare all the pieces you're going to use in it. And then there's this one little W here, which I want to talk about. If you look at the fprintf signature, which is not on the screen, but the type of this argument is not http.responseWriter. It's a type called io.writer, and it is in fact means anything that I can write to. Because in Go, one of the fundamental ideas is an interface, and they're quite different from interfaces in other languages, although they clearly have a lot in common. So in this statement, this W variable has this type from the IO package, which, by the way, was not imported. I'll come back to that. And it says anything that takes data and returns a count and an error. That's a one-line interface. And one of the things that makes the culture of Go work the way it does is that the whole system is pervaded with these little simple 1, 2, even 0-line interfaces that say, I only need to know about this one property. Can I write to you? If I can write to you, I can print to you. And so you can see printf being used to write to graphics files, to compressors, to network connections, to HTTP servers, but it's all using this fprintf through this var_now interface. This is a fundamental thing about the way stuff works. Also, in Go interfaces, you don't have to implement. You don't have to say, I implement this. You just do it. If you implement it, then the compiler figures it out and lets you call the method through there. And that's important to Go because we believe that interfaces should not be predefined for the entire world you're building, but instead should arise organically through program development. And having the compiler work out whether an interface is good or not is actually a more effective way to grow software than forcing the programmers to work it all out a priori. There are other types that are interesting. Obviously, we have the usual integer types and so on. Unlike most languages, they can't mix, so an int and an int date are not mutually interchangeable without arrangement. But the interesting part here is that we added some collections to these, which are a little more than were in the C++ world. They're certainly not unfamiliar. We added strings as a basic type. There's a map object, which you can think of as a hash map or a dictionary. And then, of course, arrays and slices, which are a form of variable length array. And as you know, Go does not have parametric polymorphism, at least not yet. And yet we found that with these very simple generic structuring objects, maps and arrays, they were sufficient for almost all the programs out there. Obviously, you can build larger things up with them. There are structs and so on. But we found having some sort of polymorphic container at the bottom of the language, well supported at the runtime, helped compensate quite a bit for the lack of a more general mechanism. But also, somewhat after the fact, we realized that these simple mechanisms being built in enabled programmers to communicate with one another with these simple mechanisms themselves. And so you don't see a profusion of different incompatible map implementations that you have to work with, or you don't find 5 different ways to represent a string. Having these fundamental types very low in the language meant all of the libraries work together in a way that we didn't really realize at the time, I don't think, but we came to appreciate it later. Now, the initial selling point for Go was certainly concurrency. When Go launched in 2009, concurrency and parallelism were perceived as being hard, difficult, annoying, even forbidden. And what we did in Go was not new in any way. In fact, it was a continuation of a line that goes back to CSP with Tony Hoare in 1978. But we came up with this word for them called Go routines, or you might think of them as green threads. The deal is that they're literally coroutines, but they are multiplexed automatically onto however many threads it takes to have no coroutine ever block the program. And so if a Go routine executes a call to a read or some other blocking operation, then all of the other Go routines on that thread are released. They're moved to other threads, or this one is moved to another thread, so that all the other Go routines are not blocked by it. And what that means, in an insight that Tony Hoare had back in 1978, is that you get to just program normally, but have concurrency glue the normal pieces together. Hence the original name, concurrent sequential processes. So here's a very simple example of a network listener. It's a function that takes a listener out of the net package, and in an infinite loop, accepts a connection, checks that there's no errors on it, and then creates a Go routine, Go serve of con, and then here's the code for the Go routine down here. And all it does is in its loop, reads requests until there's a problem like error, which will include EOF, and then it stops. So this two function program will accept all the network connections and serve them right away. And it's very simple. It's obviously not what you want to do. You want to make it a little richer. We'll come back to that. But the idea is that the overhead conceptually to deal with kind of parallelism and concurrency is really lightweight in Go. And that was a big selling point for the language. Now, in order to do this properly, you need to do communication and synchronization when you have parallel execution. And so again, borrowing from CSP, we brought in channels. You can make them, you can send on them, and you can receive on them. And at least by default, the send and the receive operations are blocking. And so this gives you a way to put a blocking operation to a Go routine to wait for an event to happen or for a message to come. And then I won't talk about it more today, but there's a thing called select, which is a multi-way communication selector, which is related to the old guarded commands thing from Dijkstra, but it's entirely communication driven. Once you take these and Go routines, you can layer them utterly simply and orthogonally above a procedural language and make concurrency easy and available to people who have been, I admit, sometimes scared of it before. So here's a slightly richer example, a variant of the previous program. This one we're going to rate limit in the sense that we're only going to allow 10 outstanding servers to run. So what we do is we create a channel, and then we start 10 servers to read from that channel. Each server will loop forever, getting a message from the channel and then handling the request. Okay? Then we have in the listener side, same loop as before, we just accept the call, check that there's no error, but instead of calling a server directly, we send the connection over the channel to the server. And the effect of this is that since there are only 10 servers, if we get an 11th call, this send of the connection on the channel will block until one of the other 10 outstanding ones completes and is available to go around its loop and come back to here. So very simple example, but we've basically built a rate limiter in a couple of extra lines of code on top of a standard example. And this kind of approach to programming really made a difference, but also, I think even more important to understand that building the libraries with this kind of capacity inside them already made it easy for us to provide production quality, ready to launch libraries that the entire programming community could use. There's a bunch of other things to go through in the language and what made it work. We spent a lot of time on thinking about security and safety. It's a much simpler language, but it's also a safer language than C++ or C. There's no pointer arithmetic, indexing's checked, it's memory safe, it's type safe. It's numeric safe, by which I mean there's no unsafe numeric conversions happening automatically. You have to say what you mean. Perhaps more importantly, any unsafe operations are packaged into this thing you have to import called the unsafe package. So the very few programs that actually need unsafe operations have to explicitly say that they're unsafe, which encourages a higher level of scrutiny. But even within the unsafe package, the garbage collector, which is precise, requires you to use the unsafe package only a certain way that it can still guarantee the other properties of the program. Now, unlike Rust, for example, Go is not guaranteed race-free, although in practice it's not too bad. But the programming model tends to make it easy to write race-free programs, but they can arise. And so we also have a dynamic runtime race detector, which we use to detect anything we missed. And as a result of the security and safety, Go has turned out to be really good for cryptography. And a lot of cryptographic stuff on the web uses it. As an example, the Let's Encrypt certificate server has now issued over 1 billion certificates, and the service is entirely written in Go. Another piece is completeness. You can give a language, but unless you can program in the language to build the kind of things you want, no one's going to care. So we made a lot of effort to build a really good set of core libraries that allow you to do things like networking and cryptography and text processing, formatted I/O. And we built a core library set built on these idea of simple interfaces. And using those with the other mechanisms we had available, like concurrency and the memory safety properties and so on, we could build fundamental libraries such that you can realistically write a program using only the core libraries that will serve a useful purpose, but can also be launched in production and be able to handle the load of thousands of things going on at once. We have seen Go binaries running with literally millions of Go routines launched internally because they are lightweight and they scale. We also have very important packages for doing Go code analysis that are used for a lot of tooling. And there's sort of a deeper point here, which is probably worth a talk on its own, which is when you're designing what goes into a language or its libraries or both, you have to balance between what everyone wants. Everyone wants every feature in the world. What you really need, versus, and also what actually is worth doing, even though it's not necessary because it's important for convenience. And figuring that out is a really critical balance. You can decide for yourselves whether we pulled that off, but we certainly tried to. Consistency is really important. You want every piece of the world to feel right. We worried a lot about consistent performance and behavior. The language has remarkably few unspecified details in its specification, neither does the library. As a result, you can compile the Go source code for a program and run it with very likely complete success, completely across binaries, across architectures, across operating systems. And in fact, to do so, all you have to do is set 2 special environment variables, the operating system and the architecture, and then say Go build. And this is honestly how people, including me, deploy programs to cloud when building on an architecture or an operating system other than their own. I typically work on Mac, but I always deploy to Linux, and we just do this. Having native code generated by the compiler means there's no JIT, things start up well. And the garbage collector, which is probably the most amazing piece of tech in the whole system, we were worried about latency, but we thanks to people on the team like Rick Hudson, Austin Clements, we got garbage collector behavior such that a multi-gigabyte heap collection doesn't stop your program for more than a few microseconds. And so at human time scale, you never see a Go program stopping even while the garbage collector is running because of the quality of the implementation of the garbage collector. Perhaps the most important part of Go's success was this compatibility promise. You know, there's a lot of churn in the early years. The language was changing constantly. The libraries were breaking every round. But in March of 2012, we issued version 1.0 of Go. And with that version, we wrote a document called the Compatibility Promise, which promised our users that we would make no more incompatible changes to the language or the library. We might add new features, we might extend things, we might fix bugs. We hope we might have to deal with some incompatibility if there's a security issue, although there hasn't been much of that. But more importantly, we just promised our users, if your code works today, it's going to work a decade from now. And it does. And this promise to the user community was a huge feature in the adoption of Go. There's actually a knee in the curve, you can see, and the adoption rate go up, because industry could now start banking on it, because they knew that if they invested in it, it was going to work. Authors of books could write books that they would know was to remain relevant a decade on. And this was such a huge part of our story. I'm kind of surprised more systems and projects haven't done this. It just seems like promising to users you're not going to break their stuff would be a very nice promise to make. And I'm a customer of a lot of companies that I wish did that. I mentioned the libraries we had to do source code analysis and so on. This enabled a whole bunch of tools. The system, when you do the standard installation, comes with a tool that includes operators for building, formatting the code, testing coverage, generating documents, distributed dependency management. And the key point here is not that those tools exist, but the library and the way the language is designed and the way the language works with the library makes it easy for anybody to do that. And so there's now a massive and ever-growing toolbox for Go programs that's been created by the open source community, which we're tremendously grateful for. So I mentioned the library, it's very well stocked. One of the things we did, though, was we chose that the packages would be named by what is in effect a URL. That meant that there would be no central authority for packages. There would be no namespace squatting. People wouldn't scramble over the first package to be named foo, because everybody gets their own namespace. If you're in your company and you're foo.com, you get to have your own Go package namespace all to yourself. In order to find things, there's a discovery site that lets you search for packages and find them. Lately, we've gone to a module system with semantic versioning backed by that. And there's also a public cryptographically signed mirror for downloading packages to guarantee some sort of safety that you're getting what you want. But of course, you can deploy it if you're on. We were actually a little late to this. I'll admit we didn't have this module system in place as soon as we should have. But I think it's worked out really well now that we've got it out there. So through all of these elements, there's a theme. And the theme is that if you want to grow a language or a system, especially in the open source world, you have to make it easy for others to come in. And that doesn't just mean accepting every pull request that comes your way. It means creating a system that's easy to work with, a language, in this case, that's easy to parse, easy to analyze, with tools that support it, libraries that can work individually but are designed to work with one another to build up larger systems, packages for high-quality tool development, easy to understand development, high-speed execution, easy deployment, easy portability, a module system that lets everyone share their code comfortably, and also a culture that encourages people to help grow together. An example of all of this is kind of an anti-example almost. When we were first putting Go out the door, we thought we'd have to build an integrated development environment for it, because that was kind of the trend at the time. But none of us knew how to do that, and none of us had the skill set. So we didn't. But in time, it turned out that was okay, because we built everything you needed to write IDE plugins. And now that there's an ecosystem with all these various plugins like JetBrains and Atom and VS Code, they all have plugins that outsiders have written for Go that makes Go a first-class citizen in the modern development environment. We didn't do anything other than give the tools to make that possible. I think that's a pretty good lesson. So with all that in place, you can grow a culture, an open source community. In our case, it has helped us build the modern cloud environment. I mean that quite literally. Open source is a massive component of what made Go succeed, and the open source community has been a massive contributor to that effort. Together, we've supported a common vision for how we think software should be written, supported, and maintained, how you think about compatibility and maintenance and honoring what your users expect, a culture of safety in your code, compatibility, portability of code, readability of code, which is generated by the tools and enforced by the culture. And so we've generated this community that works together to build a software development environment fostered by, but so much more than the language. And it's all been a lot of fun. So in conclusion, when designing a language, it's not just the language that matters. You have to put all these other pieces in place to foster a thriving ecosystem. Things have to be quick, efficient, portable, smooth, compatible, abstract nicely, have great libraries with easy tooling, easy automation, and in particular, a common culture that you can share around it. Or to summarize that even further, Go is about software development. It's not just about programming. And I think that's why it has done as well as it has. I think I'm out of time. Just about right. Thank you very much. I'm listening to thunderous applause on mute. Can't hear anything.
Thank you, Rob.
There we are.
We do have a good number of questions. Starting with, how would you think the introduction of generics will change how people write Go? Do you worry that
Could you make that the second question? Could you make the second question be about generics? I think it would have, well, first of all, it's not that it was, we didn't go in because we didn't want them per se. We didn't put them in from the beginning because we didn't understand how. We were not comfortable with it. So it wasn't that we just decided to leave them out and move on. It was that we weren't sure how to achieve what we wanted to achieve in all these other aspects if we started with a language with parametric polymorphism. And I believe that's still true. I believe that a lot of the things about the way the library works and the interconnection works and so on would have had a very different flavor if it had been a polymorphic language. And I'm not sure it would have been as good. Having figured all that out now, and over a decade of work by people like Ian Taylor and others, we now have a design for, I would say we, it's not really me, but the team has a design for a parametric polymorphism model that feels like it fits with the rest of the language. And I think we're now ready to try that. But it's going to be interesting to see whether it breaks this. It could break everything because of the change in the way that programmers will start to think about writing code this way. I'm really curious to see how that works. But it's kind of a hypothetical that I can't answer.
Okay. Next one is interesting, got voted up most, and it sort of reminds me of this statement. I don't remember who said it, I'm not a languages person, but there's no worse fights than about concrete syntax. So this question asks, why was the decision made to have variable name before type?
It wasn't really made. It was already made by languages like Pascal and Modula that we were borrowing from. I actually wrote a blog post about this shortly after because the question came up early on. C is actually the outlier in this. C is unusual in the way that it expresses declarations. And what it does is it says that you write an expression involving the variable, and that expression then has the type you're looking for. So if you want a pointer, you write expression star p, and then you say that the expression star p has type int. And that's really interesting, but it breaks down when types get complicated. Trying to write a function in C that takes a function and returns a function, you rapidly get into a maze of difficulty. And so we decided, or maybe never even talked about it, maybe it just happened, to go back to the Pascal-Algol kind of model, where you put the type, where you put the name first, and the name is out of the way, and then you can say what type the name has. And that means you have two grammars, one for types and one for expressions. But that resolves a lot of parsing difficulty around things like function declarations, closures, casting. And there is a blog post I wrote about that, if you want to look it up. But I think it's an absolutely correct decision. It may look weird to people who've only worked in C and C++ and Java, but all the other languages in the world work this way.
I do remember when I first started programming C, the way variables were declared seemed really, really strange to me. Okay. Are there any language features that you would add into Go if you didn't care about backwards compatibility?
Well, we're kind of doing that now, right? I mean, we're trying very hard to maintain compatibility with generics. I think it will happen. I miss some of the features of concurrency that some of the predecessor languages had, with richer models for concurrency that we couldn't do non-generically. So I'm looking forward to things like channel packages and multiplexers and stuff like that being available as libraries. I think that's going to be really interesting. Features I miss. I think for what the kind of code I tend to write, Ken, Robert, and I designed the language we wanted. Excuse me. So no, I don't really feel I miss anything, but I know that's solipsistic. There may be things I take out. I think there's way too many ways to declare a variable. And there's some features in the library I'd rip out with prejudice if I could. But the language proper, I think, is pretty good. It was settled on by the three of us who are very, very different people with very, very different goals, all agreeing on everything that went into it. There was no, okay, you want it, you can have this, and if you give me that kind of debate. If a feature wasn't, if a language design property or feature wasn't something all three of us agreed was right, we didn't put it in. And so we ended up with a very compact thing, but then that had this form that I think is really good. It's a very good question, and I should have an answer for it. But I think the answer is I'm just too, maybe too solipsistic about it. I don't know. I like it how it is.
Okay, and now on sort of that comes back
You have one, pardon me. One,
Yeah.
sorry, there was one. We worked very, very hard and failed to find a way to make networking and channels go together. For a long time in the early days, we actually thought the channels would work over the network, but we never found a really good way to do it. Others have tried and done better than we were able to, but that was something we had to leave on the floor. And I think it's kind of a shame because we figured out how. It may not be possible to do well, but if we figured out how, it might have been a really wonderful thing to have available. So yeah, there is that.
So coming back to the topic of simplicity, etc., there's a good question that asks, when it comes to core language design, what do you think is the optimal team size? Do too many cooks spoil the broth? I think the answer to that one, to the last part, is yes, but...
Yes. 3 is a really good number, I know from experience. Limbo was designed with 3. 1 is too small. You don't get the critical input you need with 1. We ended up being really 5 for the core language because Robert and Ken and I were joined by Ian Taylor and Russ Cox early on. And I think that group of 5 was fantastic. So that's a really good number, but somewhere in the 3, 4, 5 range is probably the ideal number.
What are the advantages of Go over other scalable languages like Erlang or Elixir?
Well, those languages are not compiled to native code. They have other strengths. They're wonderful languages, don't get me wrong. They're much better at kind of failover modeling and certain other properties, something that Go doesn't do well enough, and I probably should have thought about earlier. But what it is good at is things like it can take that CSP model and let you do the coordination using that, but then have native code for things like cryptographic calculations or network processing or things like that. So you get to mix very efficient, tight code with this nice high-level abstract model for messaging. So I think that's the advantage over Elixir or Erlang. But you know, as I say, Erlang and Elixir have advantages over Go as well. It's choose your language. You know, not all languages do everything.
Okay, and this is not a question, but a comment from my colleague Carol Morgan, who traced the source to the thing I incompetently quoted earlier. It's from Robin Milner. There are 2 situations in which people behave like animals, behind the wheel of a car and discussing concrete syntax.
Okay.
So this is probably the last question. It's got upvoted a lot, which I found interesting here. Before Go 1.14, or 1.14, I guess, why was Go structured so that projects had to be placed in GoPath?
That was because we were stupid. We didn't know what we needed to know to do it right. So one of the properties of Go that I think maybe I should have talked about a little bit is that it was designed by people who wanted to use it. And those people had a certain life experience for programming. We built the language that we wanted to solve the problems we had. We were working at Google. Google has a very, very different development model from, say, the open source world today. Everybody lives ahead. It's one code base. We're all in it together. It's a little bit crazy, but it's also very effective. So we did not appreciate, because we simply never experienced it, what it meant to work in what we call today the sort of distributed Git model of development. And as a result, we didn't appreciate how to lay out a project in a way that multiple people could share code across the network, put components together, manage projects independently. We just thought you grabbed the source code and built it. And it wasn't until we came to understand from experience more and more what that meant that the module system came to life and supplanted GoPath. So GoPath was just a hack that we thought was good enough because we didn't know better. So mea culpa, we didn't know enough. But you know, we're past that now. You know, the module system is fully turned on, and as far as I can tell from our users, very happy.
Mistakes are always good when you can fix them. And I claim chairman's prerogative by asking a question myself. So there's a lot of things that are happening implicitly with Go. Does that not make reasoning about programs hard?
What are you referring to?
Well, you gave at least one concrete example of not explicitly exporting things. Interfaces happen organically, you said. To me, that seems like it would make it harder to reason about how 2 different components interact.
Interesting, okay. Well, when it has been necessary to do that kind of analysis, we have found it very easy to do because the tooling is so good. So yes, when you look at that printf example, that W is not, you don't see the type of W as being an IO.writer inside by the time it gets to printf. You only see it as an HTTP response writer at the top. But if you wanted to analyze what's going on across that boundary, you know where printf came from precisely because it's always bound to the name of the package it came from, the FMT package. So you look up that package, you look at the definition for printf, and you've got the type. It's very easy to do that. It's so easy that, you know, the documentation processor that does automatic documentation follows all the typing stuff was written in an afternoon using the tools that we have. So you're right, the more you write down clearly, the easier it is to analyze. But I think in the modern world, analyzing programs by hand is kind of a thing of the past. Most programs of any consequence are, you know, tens of thousands, if not millions of lines. And what you really have to make work well is automated analysis. And I don't think Go has any penalties there for automation.
I guess in Butler Lamson's words, Go is definitely designed not for the precise part, but for the timeliness part of programming.
So we're getting stuff done.
Okay, so that gets us to the end of this session. And I'd like to again express our appreciation for Rob to be here. Unfortunately, you couldn't make it physically. That would have been even more fun, but it was a very entertaining talk that got a lot of feedback from the audience. So thank you very much.
Thank you for inviting me.
And now we have another break, and you should all know the drill by now, so wait until you escorted out. We continue here at 3:35 Sydney time, and I was lying before, of course. Elizabeth was not the last overseas talk. We still have Andy Tannenbaum from Europe at the end. So.